like we're live. Okay, so the goal here is I put up a problem on the screen and I want you to identify what type of problem it is, maybe get it started. Don't try to finish the problem, but try to write down an equation that might help you do each part. And so I'm going to put this on here and yeah, so I'm going to look at my clock here. So it just turned 4:40 on my clock. So I'm going to give you about 2 minutes for this one. Take 2 minutes and see if you could write down some equations or have an idea how to start each part. Don't try to finish it. I guess if any students want to, after I give you the few minutes, we could let you share your screen and I could give you a critique too. And again, we're more interested in starting the problems, not finishing them. Finishing them is just algebra. I ran out of water, so I'm going to get some more water really quick. All right, so that was 2 minutes. Do you guys want more time or not? Or should we go ahead and start talking about it? I'm looking at the chat right now. If you guys have an opinion, you can contribute, and if not, it's okay. So, okay, cool. Are you doing for all parts or just part A, Joy? Oh, okay, okay. Yep, translational. Yep. So hopefully in part A, yep, it's collision, momentum. A lot of you are saying the right things. So if I could, and we could look at it later. So for 2A, I would do and hopefully you thought of doing that, something like that. And it looks like, wait, what type of, they stick. So it's M. So hopefully you did something like that for part A and just did the math. All right, that's cool. I'm going to move that out of the way here. So hopefully you're taking a look at part B really quick. Uh, look at the masses. Look at the masses. Yep, yep. And you could see This is actually a pretty good question. You can see how I mix it up from the types that were on your book. It's pretty similar, but you do have to watch the masses and the speeds. Which way is this thing going to move afterwards? To the right or to the left? So I guess I'll pick on you, Jay. You can unmute or you can do it in the chat. Which way do you think it's going to go after the collision? Right, left, or zero? I think left, because look at the momentum initially. You have 3 MV to the left, but only 2 MV to the right. Yep. Okay, you got the idea though, right? I guess an easy way to mix this up would be you could have the rod move and impact a point mass instead, right? So you could do it that way too, and that would be same problem, but yeah, whatever. Okay, hopefully 2B center mass is straightforward. I'm going to assume 2B is automatic for you all, right? If not, whoops, I'll put something out. I just say y center mass is equal to right? It's just that. So that one's pretty easy. All right. And then 2C, moment of inertia. Oh, about the, okay. So that one's going to be tricky. Think about that one. What do you have to do for that one, 2C? Okay, 2C. Yeah, we need to find the center of mass. So that was part 2B. And then parallel axis, I agree. So I'd say whoops. Um, so use the, oops, oh, that's a weird.
The rod is massless.
Oh, cool. Oh, sweet. That helps out, doesn't it? Okay, so that saves some time. But I guess if the rod did have mass, you would do this. So all this is still correct, only it's convenient that this is 0. Woohoo!
We don't need to actually use the parallel axis term now, though, do we?
Nope.
Yeah, I
Nope.
didn't think so.
So
Okay.
notice I1 and 2, you just use the point mass formula, but you do need to know the distance from the center mass. That explains why that's only worth 2 stars. It's a lot easier if you notice that. Okay, cool. All right. And then what do you do for part 2D? Take a second to think, everybody. Give everybody a second to think before you dump anything in the chat. And okay, so go ahead and dump whatever you want in the chat now. So if we're trying to do part 2D, what would you use? What kind of technique or anything you want, okay? Mm-hmm. Well, wait a minute. Point masses, do they even have angular momentum? Isn't it just zero? How do I get the angular momentum of the point mass? So I'm going to actually write this one out. Looks like you got it. Nice job, Joy. Um, and then how do I get the final angular momentum? Yep, r sine theta. What's theta in this case, Nick? Okay. So you're going that way. I got you. Yep. And so we're going to do I. And notice we should have, so it's kind of walking you through everything. So that's not too bad. All right. Very good. Nice job. Should I try another one, everybody? A new problem? I'm going to. All right. So let's kill that. And so I'll bring it up and hide it from you. Oops, that's the wrong one. Where are we at here? All right. Let me pick a different one. Whoops, solution. Crap. Let's try. I got one. This will be good. Okay. So I'm just giving you a second to do it. If you want, you can literally just scribble on a piece of paper right in front of you. So we've got a question here. And I know you've probably done some of these before, but that's just a sign that you're going to do well. All right. And I think I'm getting lost with some of these files back here. There we go. Whoa, where did it go? Sorry about that. There we go. All right. So hopefully you had a second to figure this out. She first travels to the right. That says V initial is greater than 0 with an greater than or equal to 0. It looks like she starts from rest. So this tells me V initial equals 0. And so she travels to the right with an acceleration. So this actually tells me, sorry, let me clear this out. That part tells me V initial is 0. This part says travels to the right. So that says A is greater than 0, implies positive slope of 2 until she hits 8. So okay. That's a slope of 6. Okay, so that's going to go down, let's see. She goes down 6, 246 over 1. And then down another. Oh my gosh, I'm going to have to move this, aren't I? Crap. All right, I'll clean this up and then move down. And then, whoops. The green part is just, it goes there until 8. So I need to clear this and move down. We expect to see something that looks like this. Three, 6, 10. There we go. So hopefully that's not too bad. That's a good warm up on the plots. Maybe I should have asked you more for thoughts. I don't know. Hopefully that's what you were thinking. Did that work out? Everybody good on that? Okay. Sorry if I took over too much. I'm just trying to do the best I can here. So my bad. Let me know if I could do better. All right. So let's go ahead. I'm going to find another problem. And I had one queued up here. Whoops. So going back to what Jay asked, let's go take a look here. So maybe I didn't draw it perfectly. I don't know, but the idea here is, and I gotta, you know what? I've got the solution. It is. I think it looks something like that. And I'm not sure, maybe I drew it the wrong way before, but so something like that. Yeah, I was a little sloppy and I had to move things around. Sorry about that. Whoops. Get back to my. All right, let's get back to this one. So we're done with that one for now, maybe. Let's go try this one. So again, I'm just going to check my clock here, give you a minute to look at it. And my apologies if I'm not talking too much, but sorry about that. If this is bad, we'll mix it up. Or you can take off. It doesn't offend me. I'll give you about 30 more seconds. All right. And so hopefully your thought process here, you know that I about the rim is equal to I about the center mass plus mass total times radius in this case squared. I hope that jumps out at you, right? And notice this is known. This is not known. This is not known, right? Because in this case, M total is equal to the mass of the ring, which is known, plus 4 times the mass of a spoke. And so furthermore, we know I center mass should equal 4 times the moment of inertia of a spoke plus, whoops, I center mass of the ring. Let me spread that out a little bit. And so just keep going with that. Hopefully you caught that the moment of inertia of a spoke would be 1/3 times the mass of a spoke, which I'm calling little m here, times r squared, plus the moment of inertia of the ring would just be mr squared. And I think at this point, this is known, this is known, this is known. So here we know everything here. We know this, and we know everything in this except for little m. Now look at this I center mass. We know everything. Whoops, this should be a capital R, I think. We know everything here, everything here, everything here, except for m. So if you look at this, you know everything except for little m. Solve for little m. How was that one? Is that good? Okay. Let's take, okay, got it. All right, so let me find some more. Is this what you guys want to keep doing? I figure it's as good as anything, right? But okay. Let me pick another random one. Okay, I got one picked up. Come on, computer. All right, here we go. I'll start the clock. You could tell I was on a Battlestar Galactica kick if you know the show. And so I'll give you about another 30 seconds and then we'll discuss it. So let's call that good. Any thoughts? Anybody want to chime in there on chat or unmute? Either way is fine. If you want to talk about your reasoning, is cool. If not, that's right. The forces have to be balanced if you move with constant speed, right? If you move with constant speed, The force, there's no acceleration. Now, I should be careful here. If you move with constant speed in a circle, you could still have a force towards the center of the circle. But assuming you're moving left, right, or up, down with constant speed, you're not accelerating. So in that case, they exert the same force magnitude, I guess I should have said, but whatever. How about this case? So Jay contributed last time. Somebody else go ahead. Let's see. Going to the left. Yeah. And then what's your reasoning, Jose M? Did you I don't know if you heard that. I don't know if you had any what reasoning are you using, Jose? Yeah, okay. So I was looking for, yeah, like Newton's second law, right? So both of these are Newton's second law questions. So if you're accelerating that way, that force has to be bigger. So if you're accelerating to the left, this causes a net acceleration. Now, sometimes this problem is given, but notice in this problem, I'm assuming the rope has non-negligible mass. So this is the same thing as that problem where there's 3 blocks and you're pushing them. If you apply a force to the right, it's the same idea, right? So if you're pushing 3 blocks to the right, you use Newton's. If you're comparing the force of this one here and this one there, you use Newton's second law. Now, if you're comparing these forces right here and right here, you would use Newton's third law. So that's what I want you to get out of this. All right, let's move on. Let me find another one really quick. Okay, let's go out here. Let me do share screen. Come on now. Here we go. And by the way, I don't even think A. I think this is an unknown. And I could be mistaken. So I think it's over specified. Assume that acceleration is unknown for right now. Yeah, it is, because down here we're going to figure out the minimum. So we don't know the acceleration either. So I'm just giving you a minute to think. Give you another 20 seconds here. All right, so I'm going to go ahead and call it. My apologies if I'm going too fast. Hopefully, you immediately thought free body diagram because you see things they're talking about forces and accelerations. Hopefully, everybody says FBD. In this case, read this carefully. It says prevent block mass M sliding downwards. Can I use a system FBD? Again, can I use a system FBD for this problem? Yes or no? I'll see. I'll open up the chat. Anybody that's wants to can respond. Oops. Okay. Maybe you don't remember. Whoops. Or can it that you can because they're moving as a single unit without slipping. So if it was sliding downwards, you couldn't do that. They wouldn't necessarily have the same acceleration. Ooh, that would have been a good problem to put on your final. Oh, well, I forgot. But yeah, I'm going to blow this up now and get nasty with it. Hopefully you did free body diagram. So what's most important at this point, remember, most of the points for this is getting these arrows right. So I'm going to kind of put the forces here for each block. So that's a normal force and a friction. Notice on this block, they're pushing back by Newton's third law, the same amount. So the blue ones are on 4m, the green ones are on little m. And then there's probably a normal force here, about the same size. And I guess we're going to have a thrust force here, right? A force forwards from the thrust. Now, so if I tried to label those, let me see if I could go in. That's the thrust force. This is the normal force from the floor. This is 4mg, while this is just mg. And then I would call this one normal force 1, 4, just because it's between these. And I would call this friction between 1 and 4. That's what holds this block up. This, by Newton's third law, has the same magnitude, opposite direction. Same here. All right. And so if you wanted to do the system FBD, it's a lot easier, right? The system FBD would look like, what am I doing here? The internal forces, if I was doing the system FBD, these forces would disappear. So if I was doing the system FBD, notice you'd get a 5mg. You'd also have a thrust and a normal force, I think. And so that would be the system FBD. After that, force equations do it. This one's actually pretty simple. There's no angles. All right, so that's a good one to practice. I'm going to say from there, what do we use here? One last thing. Minimum thrust force. Hopefully you thought Because of this word minimum, that's what allows us to say it's equal to mu static times normal force. If it was not the minimum thrust force, for example, let's say we did twice the minimum. I bet that's a concept question at the bottom of this page. Now consider the frictional force between the blocks. If we use twice as much thrust force, how is the frictional force on M affected? Take a second and think about it. Yeah, Jay, with the system, friction is internal. There was no friction between the ground, I think. Let me look. Frictionless surface. Oh, okay. All right. You write down the free body diagrams at the minimum thrust force. That allows you to use mu static N, and then you just solve for T. Right? So typically what I would do is, to be honest with this problem, I would do a system FBD if I was trying to get this done fast. And then I would use an FBD for M. And when you do that, you're going to get two sets of equations. This one says thrust equals 5 ma. This is unknown. This is unknown. Well, now you do FBD for this one, and you get mu static normal force 1,4 equals ma. But now I still have unknowns. This is the same unknown, but I have a new one, so I need another equation. Well, I also, whoops, sorry, mg. That's the vertical force equation. So now I know the normal force there, and then I also know, whoops, in this equation, normal force 1,4 equals ma. So notice I have three equations, three unknowns. Problem's trivial. Is that good? Right on, right on. And again, these are all on the practice sheets anyways, but yeah, so we can go out, and if you like these questions, you probably noticed up here, if there's something that you don't understand, make sure you write this down in the problem number, and you could check it later if the lag is shitty or something like that. You know what I mean? So if at any time I'm doing something here and the computer lags, or you want more thorough, remember all these are online for you as well. Okay. So write down the tests, and I think you can see that. All right. Let's go do that concept question now. This. We're doing this. Okay. If I use twice as much thrust as the minimum thrust required, how is the frictional force affected? What is it? I'll give you 30 seconds. I see one vote there. What do you guys think? Is Joy right? Okay. See a decrease. Anybody else? Thoughts? Interesting. It's not changed at all. What changes is this. Let me scroll up. If you're at the minimum, friction equals mu static N. If you go beyond that, remember, what is the free body diagram? There's a normal force here, there's friction up, and mg down. If you apply more thrust force, you get more acceleration, you get more normal force, but you're not accelerating up and down. So these two must always balance. So F equals mg as you go faster and faster doesn't matter. What happens is this is no longer true. This is no longer true if you apply more thrust. Basically, if you're at the minimum, then mu static N. If you're greater than the minimum, you're not on the verge of slipping anymore. You've got so much normal force. You've got much, mu static N is the maximum possible, but you don't need all of it. Is that making some sense? Or any questions about any of that? You probably remember that now because we hammered that in lecture a bunch of times. I think about the one, remember the one where I put the eraser in the aquarium and then spun it, and then the eraser would stick to the side, and then if you spin it really fast, the frictional force didn't change because it's still just supporting the weight. We saw that one with a demo. Okay, I'm going to bring up a new question now. Whoops. Get this one here. Looking at question 1. I'm teaching right now. What is it?
If you hear something steaming or the water's boiling, that means the water is boiling for the mac and cheese.
All right.
So you could put the mac and cheese in.
Okay. All right. So hopefully you had a second to look at this one. Hopefully it's not PTSD from early in the semester. I kind of got lost there. My kid came in, one of them. Let's see if there's any thoughts. Yeah. Hopefully you recognize this one as one of these problems where you get the volume or area and write it algebraically, and then do basically a conversion factor. So in this case, it says something about the sidewall of the cylinder. I need that one. So I know from the workbook, I know that the area is going to be this distance right here. Which is 2 pi r. That's the distance around times the length. And that's the area of this gray shaded area. All right, so now I have my area that's basically in meters squared. So notice I have this piece. If I multiply this number by this area, that gives me grams per day. And now after I do that, it says per second. So I'm going to have to convert. All right. So let me go ahead and do this one here. And I need just a little more room. So I would say, I'd say area equals 2 . Okay, and then I know 10.0 times that area gives me a number in units of grams per day. Then convert 1 over day times 1 day per 24-hour times, 1 hour per 3,600 seconds, et cetera, et cetera. Actually, that's it. And then, so you just multiply by this conversion factor, whatever that is. So up here, you'd multiply or basically divide by 24 times 3,600, and you're off to the races. All right. So, any questions about this type of question here? Is that okay? Or I might pause for a second. I'll leave that up for just a second. Then I'm going to stop the screen share to see if anybody has any questions about that.
I have a question.
Yeah, go for it. Is that Sean?
Yeah, it is.
Yeah.
What originally messed me up with this problem when we first had it was I couldn't stop thinking about the very end of the cylinder.
The
How
end
that,
cap.
yeah, how that was included in the thing.
Oh, and so whoops. Oh, crap. Oops. It says ignore that.
Oh,
Does that help?
yeah, I guess I just
The
stopped
other,
before I got
and then if you did, right, there's no reason you couldn't just multiply by pi r squared here, or add in pi r squared, excuse me, times 2, because there's 2 end caps. So if you wanted to include the end caps, that's how you would do it.
Okay.
But
Yeah.
notice that I think that's going to be pretty small, because this, look at this. This is an inch, and this is 3 meters.
Yeah.
So, right, if this was drawn to scale, it would look something like this, where it's super long and the end is completely negligible. So that's why I said ignore the end caps, because literally they are negligible. If you stick in, this is like 0.0008 meters, and this thing is going to be crazy big because this is at like 3 meters times this junk.
Right.
Does that help? Oh, and then you got to square it. Okay.
Yeah. Okay.
Is that good?
Yeah.
Other questions on that, or no? Or is that good enough for now? It was this. You got to know to, and you're probably better at that now. Sean, are you better at this problem now or not?
Oh yeah, definitely.
Yeah. Okay. That's cool.
I just didn't read all the way to the end.
Yeah, you're just a better reader now, right?
Yeah.
All right, that's cool. I'm gonna open up another one unless anybody else has another question there. Yeah, I mean, all the old tests are, yeah. I think this is pretty good. You get, like, I would say that force problem was pretty easy because there was no angles, but maybe conceptually there was that tricky part, right? And so you're probably going to either get some tricky conceptual or annoying technical, but I tend to stick to more, kind of generic problems. Let me see if I can find another one for you, okay? I think this is pretty good. These are my tests, so this is what it's going to look like, right? Let me share my screen. No, there aren't any old final exams. Yeah. The only material that's not on the practice tests online is chapter 13. But I know from experience, my final exam questions out of chapter 13 look nearly identical to the chapter 13 workbook problems. Got it? So if you're wondering what's going to be on the test out of chapter 13, the workbook problems or something similar where I move it around. And then the old practice tests or the workbook questions for every other chapter. Let me keep going, do another one. All right. I'll give you a second what you would do. Yeah, I mean, the more old exams you do, like if you do the homework and then do the old exams, just like every other test in my class, I'm telling you, you're going to be lights out on this thing and just kick ass. So, yeah, it's the same procedure to study for this online test as it is for every other one. And don't forget, you could start making your kind of review sheet too. I'll talk about that after this problem. Let's do that after this problem. Let's take a look at this problem here and think about what you would do. I'll give you a couple more. I'll give you another minute. Okay, another minute. Actually, I'll give you a minute and a half. So I'll stop when my clock says 5:33. There we go. All right, looks like it's that time. So hopefully this is screaming out to you as a chapter 12 problem, static equilibrium. You got pivot written right in there, and it says reaction force in part 1C. So if you don't think static equilibrium, you haven't done all of chapter 12 yet, and that's fine. So you can get on that. But now let's take a look here. You know that there's going to be a string tension coming down this way. You know that there's a weight of the rod acting right at its center. Actually, I want to undo that. And then you could tell there's going to have to be a large reaction force at the pivot. Now, we don't know. Is it going to hold it straight up? Probably not, but it's going to need a large upward component, right, to balance some of these. And now think, which way is the X component? I argue it's probably going to be this way. And now the thing that I don't know, we don't know that it's actually going to be right in line with this thing. It might be, but I'm just going to kind of exaggerate this a little bit. It's quite possible that the pin is exerting a force not the same way. So it might be like this. It might be off at an angle. And we saw this in the simulation, or you'll see it tomorrow, where the reaction force doesn't exert a force along the rod. It could be off in some weird direction. So this is quite possible here. Now, because that's getting pretty busy, I might erase this one. I just know that there's going to be an RX and an RY. Okay. So now, all right, it's already getting busy. So now we got to get some angles in there. Well, if this is theta, then this is 180 minus. And then you might have gotten stumped, but hopefully you caught this. This is 3/4 L. And so is that dotted red line. So that means this angle up here is also question mark because it's an isosceles triangle, right? So now in this case, we know question mark times 2 plus 180 minus theta equals 180. And I'm getting lazy with my degree symbol, but I'll try and put it in here. So this drops out, question mark equals theta over 2. All right. There we go. So that's that. I kind of started sketching out this. So if I want to get the tension in the cable, what should I do, everybody? What's probably the easiest way to get this? Forces or torques? Yeah, I think torque is probably going to get you there fastest. Okay, Phil, since you were crazy enough to respond, I'll pick on you. What point would you choose as the pivot? Because when you're doing chapter 12 and torque, you get to choose the pivot point. What's the choice of pivot? Yeah, I agree. In this case, if I choose the pivot as my pivot, which forces drop out? Yeah, exactly. And then, so that's the logical order. And so then how do you get this part? Somebody other than Phil. Maybe you could contribute to the chat, somebody other than Phil. Let me move my chat out of the way in case that's blocking you. I want the reaction force. What should I do? Yep, force equations. And then, hey, everybody, what if I had screwed up and pointed this to the, what if I had drawn it the other way? Would that be a problem if I had drawn it the other way? Let's say you didn't realize. Yeah, and so what would that mean, Nick S? Would that be a problem if it came out negative? Nope. You just put an absolute value and say, okay, it's this magnitude to the left. Nice job. Nice job. Any questions about that? I'm going to go ahead and pull up the solution to this one to see if there's anything else, since we're still learning this material. See if there's anything else that I forgot. Whoops. Let me find it. What was that one? I just like 19.3a. That's depressing. You know, so here's the thing that you guys are probably going to notice. Every semester you get this group right here that's all at the ABs. Then there's a long tail. And unfortunately, due to coronavirus, this is pretty much all gone. So this is what the class looks like now. So you're all going to get these. So don't worry about your grades too much, right? Study. Yeah. All right. So let's go look at this problem. And then I'll catch up to the chat here. Oh, look at this. This is another way to do it. So you might recall, if you didn't notice that the triangle is isosceles, you could do the same thing I did with the drawbridge problem, right? And there's the torque equation. We kind of talked about that. You could see I drew a couple of different ways to split this up. Oh, this is probably useful for the force equations, right? So you could pick this one up later. It looks like I beat the crap out of it. You might notice that you could probably do a law of cosines here, right? You could do this. Oh boy. Yeah, whatever. That's good enough. Oh yeah. Oh, look at this. Watch out for this. This I don't think I mentioned. So let me go back there. Look at this. So in this case, you got to remember rx squared plus ry squared to get the magnitude. So if you want the magnitude, so that was worth looking at. Don't forget that. And then I'll go check the chat. Yes, you could still do the chapter 11 through 13 quiz, but I'm not going to give any extra credit for it. It's there, and I put it on as practice problems. No automatic A's. Sorry, Jay. Nice try. And then Alexis, that's your question. You can still do it for practice. It's still good practice, but whatever. I'm not going to make it worth anything. So if you don't want to do it and you want to just do practice exams, do practice exams instead. All right. Let me find another question for you. All right. Okay, let's take a look at another one I found. Whoops, where did it go? Here's one. Oh, that's exactly the other problem I was suggesting earlier, isn't it? So Alexis, since you're just joining us, what we're doing is I'm bringing up random test questions and then having you try to just look at them and identify the techniques applicable, et cetera, and what you should do. All right. It's not so important to solve the whole problem as it is to start the problem. And then obviously you could cheat and kind of look up here and know which test. So more important is if I am laggy or bad and you want more information, you could go look at the test and notice it. So, but yeah, if you want to make it kind of a simulated test environment, see if you could start this. And to that end, I'll start the class in a minute and a half to look at this one. So at 5:45, we'll take a look at this one and think. Where's my chat? That's right. Alexis, you can use conservation of energy anytime conservation of energy applies. So if you're talking about Alexis, a final exam question, like a projectile problem, and you find a way to solve it with conservation of energy, go for it. Usually the issue with kinematics problems and solving them with conservation of energy, most kinematics problems have time either asked for or supplied. If you're going to incorporate that information, excuse me, if you're going to incorporate that information, you usually need kinematics. So you're welcome to do it if it solves the problem, but I doubt it will. All right, so you had a second to look at this one. I'll open up the chat again. What do you think? Is translational momentum conserved? Come on, chat. Where are you? Chat disappeared. Whoops. There it is. That's right. Why? How come, or why is it not conserved in this case? Either Alexis or Joy. Yeah, I would say pivot is better. So Sean, it's not the fact that it's not in space. Yeah, not exactly. During the collision, the pivot exerts a whoops, wrong way. The pivot is going to exert a force. Oh, now I got to think. Oh, maybe it was the right way. The pivot, yeah, so the pivot exerts a force on the rod this way, and then the rod is exerting a force on the pivot as well, I think. So, and that's going to keep it from conserving momentum. So this is false. What about angular momentum? So somebody other than Joy or Alexis, what do you think? That's correct, Sean. All right. So the pivot may have a force, but this force cannot exert a torque. That's right. It's not because the pivot is at the center of the rod. It's because the pivot exerts no torque. There's a difference, right? The pivot can't exert a torque because it is at the line of action for any pivot force runs through the pivot itself. So it's not because it's at the center. It's just because it's a pivot. Alexis, you good with that? Yeah, because the same thing would be true if you did it like this, right? The pivot would exert a force, but it exerts no torque. How about kinetic energy? Is energy going to be conserved here? That's right. False. We lose energy in the deformation of the clay. Lose energy as the clay is deformed. Nice job. Okay, so now how would you do this? What type of problem? Yep. L initial equals L final. And then what's the moment? Do I need the center of mass in this problem? Do I need center mass? No. If it's in free space, you need the center of mass. Like Sean was saying, if it's floating around out in space, you wouldn't need, or you would need the center mass because that's where it pivots, right? That was like the earlier one. So in this case, it's pretty straightforward. It's MV R perp, and I'll call that M1, plus I of the rod 2 omega 2 initial, let's say. I'll call this V1 initial. And after here, it should equal I total omega final. All right. And then this is going to be I2 I'll call it X squared. And notice this right here is going to be an X, where X is this distance. Oops, that's sloppy. Right? And so we know X appears on this side, and what are we solving for? X. Oh, and notice omega final is given. And it's still spinning in the same direction. So that means it's still positive. All right. I just babbled a bunch. Is that okay? Is this helping? I'm going to stop this. Well, yeah. I'm going to stop the share for a second. Does that make it some sense how you would handle that one? So far, so good? Cool. What do you think? Are you starting to feel like you can do a couple of physics problems? Like you kind of know a little bit, right? I hope. I mean, that's the goal, right? Yeah, it takes a while, but after this test, you can learn anything pretty much. So let's go back. There was another question on that at the bottom of that page. Ooh. So let's take a look at this one. I'll set the clock here. Oh, it rotates. Oh, I love it. This is a good one. All right. So let's open this up to the chat, and you can either dump it in the chat or unmute. Any thoughts? Let me get this thing out of the way here a little bit. What do you think? Will it lose the same amount of energy, lose more energy? Okay, Alexis, go for it. If you want to unmute, just talk and explain your thought process, okay? What do you think? This is good practice for an oral exam, right? Having to kind of talk through your reasoning.
No, I kind of just thought one was better and just chose it.
Oh, which one do you think?
Well, initially I chose was the one where it says the absolute value of the change in energy in one was greater than the absolute value in the change of energy of two.
And why did you think that?
I thought that since it rotated the other way around, that would mean that well, I thought that a lot of energy was lost if that happened. So that's why I chose that one.
Okay. Let me see if anybody else has any thoughts. Does anybody else? Joy, why do you think they're equal? And Phil. Go ahead, Joy.
For some reason, I feel like it's separate from the actual rotation, the loss of energy. I don't know why, but that's just my impression.
Okay. How about this? Do you agree in both scenarios, the final energy value is the same? Does that make sense?
Yes.
Right? So now, in which case would the clay have to be moving faster?
The one where it rotates the opposite way?
That's right. So do you agree that had more initial energy?
Oh.
I did not expect that. So notice nobody got this one right. The idea was to make it rotate the other way, you clearly need more initial energy, right? Because otherwise you wouldn't have enough momentum to cause this thing to reverse. So because they both have the same final energy, and so this one is it's got to be this by a huge margin, right? You're going to lose a lot more energy in the second case. So, oh well, yeah, exactly. Same final, different initial. And so I thought, yeah, okay, whatever. That was cool. All right. That's kind of a fun question. So yeah, there's probably going to be some conceptual question on your final that gets you. Because every year I do it. I find one that just gets people that's actually straightforward, but you might not see the right way to look at it. So don't stress out over that because they're usually not worth a lot of points. But sometimes the conceptual are the hardest. Well, 5:55, you know me, I love to take a break right about now. Does anybody, should we just go ahead and do that for a couple of minutes, come back, and is this helping? Just give me your opinion, either with a thumbs up or a chat comment. Okay, cool. Cool. All right. So I'll come back in a minute and we'll just do more of this. Feel free to do whatever. By the way, I told Trey to not bother showing up today. I guess I didn't realize people would actually show up. So I was just going to answer questions. So if you're wondering where Trey is, it's because I told him not to. So sorry about that. I should have told him to come in. All right. I'll be right back and then we'll just do some more. All right.